In 2019, a fintech company discovered that their general ledger was out of balance by several $1 million. The discovery came during a regulatory audit. The accounting team had noticed something weeks earlier, but assumed it was a replication lag. It was not. 6 months before the audit, a data engineering team had written a migration tool to correct historical transaction records imported with incorrect dates. The tool updated the affected entries. What it did not do was apply the offsetting entries the bookkeeping system required. Every corrected debit had no corresponding credit. Every corrected credit had no corresponding debit. The tool had been written by engineers who understood the data structure precisely. The table names, the column types, the relationships between records. Nobody had told them about the bookkeeping invariant. Nobody had written it down anywhere. A consistency invariant is a rule that must always be true about the data. It must hold regardless of which system writes, which operation touches it, or how the current state was reached. Not a rule the database enforces. A rule the data must satisfy. An account balance that must never go negative. A ledger where every debit must have a corresponding credit. An order total that must equal the sum of its line items. An event log where no entry can precede its cause. These are invariants. They are the conditions your system depends on being true in order to function correctly. The distinction between an invariant and a database constraint matters. A constraint is something the database enforces, a not null rule, a unique index, a foreign key. If a write violates a constraint, the database rejects it. An invariant may have no corresponding constraint. It may live only in the application code that was written when the rule was understood. It may live only in the knowledge of the engineers who designed the original system. And it will hold, reliably, invisibly, until something writes to the data without knowing the rule exists. That is the failure pattern, not a bug in a system that knows the invariant. A write from a system that does not. 3 situations produce this reliably. The first is new code paths. A system grows, new services are added, new teams write against the same database. The engineers who built the original system understood the invariant. The engineers building the new feature were never told. The new code writes data correctly from its own perspective. It violates a rule it was never shown. The original system then fails in ways that seem disconnected from the new code, because the failure surfaces downstream, in the logic that reads the data and assumes the invariant holds. The second is direct database access. Application code enforces invariance by controlling how writes happen. A write goes through a service layer, a model, a validation function, all of which know the rules. A direct database write bypasses all of that. Migrations, administrative scripts, bulk imports, debugging operations. These frequently touch the database outside the normal write path. They operate on the data without invoking the logic that protects it. Invariants that are perfectly maintained by the application layer are invisible at the database layer unless they have been encoded as constraints. The third is migration and backfill operations. These carry the highest risk. A migration corrects historical records. A backfill populates a new column. Both touch large volumes of data, often written quickly and under time pressure. The engineers writing the migration understand the change they need to make. They do not always understand every invariant the records they are touching participate in. A migration that is correct in isolation can break an invariant that spans multiple tables or systems. The failure does not surface immediately. It arrives when something downstream reads the affected records and encounters a state it was never designed to handle. 3 things address this. The first is explicit invariant documentation at the data level. Every consistency invariant should be recorded as close to the data it protects as possible. Not in a wiki, not in a runbook, in the schema definition, the migration files, the model layer, wherever an engineer is most likely to see it before they violate it. A comment in a schema file that says, "Every debit entry must have a corresponding credit. Do not write to this table outside the ledger service." That annotation is more effective than the best written architecture document because it is present at the moment when it is needed. The second is database-level encoding, wherever it is feasible. Some invariants map cleanly to database constructs, check constraints, triggers, generated columns. Not all invariants do. But for those that can be encoded at the database level, the rule holds for every write path, application code, direct access, migrations, and any future service that does not yet exist. A database-level constraint does not require the writer to know the rule. It enforces the rule regardless of what the writer knows. The third is invariant verification as a step in every migration. Before a migration runs against production data, run a query that confirms the invariant holds in the current state. After the migration completes, run it again. If the result changes, the migration broke the invariant, and you know before it propagates further. This does not require a formal framework. A query that returns 0 rows when the invariant holds and non-zero rows when it does not is enough. Running it before and after is the difference between catching a broken invariant during the migration and discovering it during a regulatory audit 6 months later. The fintech team rebuilt the missing offsetting entries from transaction logs. The correction required a full reconciliation of 6 months of affected records and took several weeks. The migration tool was not the problem. The absence of any record that the invariant existed was. Consistency invariants are the rules your system silently depends on. They hold for years because every code path that writes the data was written by someone who knew them. The moment a migration, a new service, or a direct write touches the data without knowing them, they break. Nothing in the database catches the violation. The data looks valid. The system keeps running. The invariant is gone, and the failure arrives later, somewhere downstream, in logic that assumed the rules still held.